Gentlemen, take your seats. Does civilization have a promising energy future? That's our question of the weekend, and we always like to feature a panel on the first night of Wonderfest to address the really big questions that take more than one person to answer or address. Tonight we have a very stellar group of people to talk about energy. They've all made their name in energy. And almost like the panel we had for the mind duel, they have varied skills and focuses here. So I think we've got energy pretty much covered with this panel. I'll begin by introducing people to from left to right, I guess. All right. First, we have Lynn Orr. Yes. Well, I don't want to. I want to go first to Mike, I guess. Let's start with Mike. Okay, let's start this way and go. Okay. Everybody's here. All right. Mike McGehee, who closest to me here, I think, is Associate Professor of Materials Science and Engineering here at Stanford. He earned his PhD in Materials Science from UC Santa Barbara, and he did research there on polymer lasers. Mike has won numerous awards for his research into polymers and solar energy. I'm thinking of social networks. But he does have a lot of that, too. Including a National Science NSF Career Award, the 2007 Materials Research Society Outstanding Young Investigator Award, and the 2007 Moore David Au Innovators Award. So please welcome Mike McGehee. And you've already met Dan Kammen, who got half the answers right on the mind duel. And half wrong. And somebody pointed out to us, by the way, here that it was a tie because the audience got 8 points, too. So I'm just saying. So Dan Kammen is Professor of Energy Resources Group at the Energy Resources Group at Berkeley, but also at Cal. He is Professor of Public Policy at the Goldman School of Public Policy, Professor in Nuclear Engineering. Fission or fusion? All of the above, and and founding director of the Renewable and Appropriate Energy Laboratory there, and he earned his PhD in physics from Harvard, joined the Cal faculty in 1998, and he's a fellow of the American Physical Society and a permanent fellow of the African Academy of Sciences. Welcome, Dan Kammen, again. And I'm going to skip our team leader, I should say, until I'm saving you for the end, and move to Per Peterson. Per is the professor and former department chair of nuclear engineering at UC Berkeley. He also manages the UC Berkeley Thermal Hydraulics Research Laboratory and is a member of the Energy Resources Group at Cal. He earned his PhD in mechanical engineering at Berkeley and has served on numerous technical committees and has edited some important journals in thermal hydraulics and nuclear engineering. Ladies and gentlemen, Per Peterson. And Franklin Orr. Lynn is the Killeen and Carlton Beale Professor in Petroleum Engineering with Stanford's Department of Energy Resources and Director of the Global Climate and Energy Project here at Stanford also. He earned his PhD in Chemical Engineering from the University of Minnesota and joined the Stanford faculty in 1985. And his recent research includes the study of carbon sequestration. Why they have to use black horses, I don't know. He has received numerous honors, and his membership of the National Academy of Engineering. Ladies and gentlemen, Lynn Orr. And last but not least, I don't know why I'm calling you team leader, but you are sort of the moderator of the panel. Stephen Chu. Many of you already know him. He's perfectly qualified to moderate the panel because, not only because of his expertise in energy, obviously, because of his ability to bridge the two campuses, Stanford's culture and Cal's. Professor Chu has been a key member of the physics departments of both Stanford and Cal, now professor of physics and professor of molecular and cell biology at UC Berkeley. He's also director of the Lawrence Berkeley National Laboratory, and he earned his PhD in physics from Cal. Soon after, joined the AT&T Bell Labs and did some groundbreaking work in cooling and trapping atoms using laser light. It was for this work that he received the 1997 Nobel Prize in Physics. Stephen Chu, ladies and gentlemen. I will just say we don't have a microphone for each of you, as you probably realize now. pairs of you are sharing a microphone. The microphones don't have cables on them, so that means that you can easily, if you need, merely take them off of their stands and hold them to get them closer if you want, or you can just lean into the microphone. If the audience is having any trouble hearing you, I'm sure they will let you know, and I'll help out with the microphones. So, Dr. Chu, I'll turn it over to you.
Okay, thank you. I just prepared 4 slides, and so bear with me. I hope it can be brief because it's late and well past my bedtime. So the question before this panel is, does civilization have a promising energy future? Now, that question might mean different things to different people. For example, this summer, the price of gasoline was pretty high, and to many people, probably to most Americans, a promising energy future might look something like this. But it's actually, we're going to tilt the discussion to a little bit different, and it's not the price of gasoline we will be talking about, but there are larger issues, and this is the larger issue. How do we go forward in a development of world prosperity and yet still have enough resources on the earth and enough energy to do the things we'd like to do, and even if that's possible. So many of you are familiar with this movie, the Titanic, and so I want you to imagine something. Instead of this is www Titanic movie, but imagine Titanic the sequel. So in the sequel, the Titanic is about 1 billion times bigger than the original Titanic. And unlike the Titanic, it isn't actually steered by a captain. There's a whole bunch of captains. And in fact, the captains have all sorts of constituencies point at them, asking them to do various things. Okay? So imagine this. Maybe 2 decades ago, some people on the Titanic kind of look ahead and say, looks like there's an iceberg way ahead. Shouldn't we be careful? Then 10 years go by, and the iceberg looks a little bit more apparent. And another 10 years go by, and most of the people on the ship see this iceberg. And then the engineers on board go to this consortium of captains, and they say, this is a very big ship. It will take about 30 years to turn. Meanwhile, it's still going full speed ahead. Now, there's all sorts of issues. It's the maiden voyage of Titanic II. And as in many maiden voyages, there are things that are going wrong. For example, in the 3rd class, there's a kitchen that's on fire. It's a really serious business. You've got to put the kitchen out. The air conditioning in 1st class doesn't work so well. That's even more serious business because they're 1st class passengers. And so on and so forth. So there are all these things, all these daily, yearly, in the vernacular, the stresses that are taking the attention of the captains of the ship. But still, it's full speed ahead because there was a consortium of companies that built the Titanic, and they want to book more passengers on future voyages, and they want to set a speed record to get across the Atlantic. So it's good for them economically to just go full speed ahead. So they're saying go full speed ahead, not to worry. But the iceberg is getting bigger and bigger. And then the engineers say, not only is it going to take 20 or 30 years to turn the ship, but I think there's no way we're going to avoid it. There are 2 choices. There are a bunch of choices. We can hit it dead on, or maybe we can turn it and get a glancing blow. And then a big debate ensues, because by this time, all but 5% of the population sees the iceberg. And what they say is, well, if we turn really hard rudder, to turn to the left as hard as we can, this is going to be bad. The ship will rock. All the china in 1st class will break. Things will get disturbed. People will get nauseous. This is not good. And we don't really need to turn it hard full rudder. Maybe we can just ease it. But then there are other people who say, no. You've got to turn it hard full rudder. That's the only way you can do it. And so there's this big debate. Okay. And so that's the movie. We don't really know how it's going to end. This is the iceberg. The iceberg is, this is the temperature of the Earth over the last roughly 1,000 years. And this solid curve is the average of the temperature. And so what has happened is that the temperature has risen roughly 0.8, 0.7 degrees centigrade since 1800. And there are some people who predict that in the next 80 to 100 years, the temperature of the globe might increase. The predictions, the smart money is somewhere between 2 degrees centigrade and maybe 5 or 6 degrees centigrade. Big error bars, because we don't really know how the movie's going to end. However, if it increases by 6 degrees centigrade, that's not good news. Why is that not good news? Because 6 degrees centigrade colder was between us and the ice ages. Now, the ice ages was a very different world. 6 degrees colder, and all of Canada and the United States down to New York City, Pennsylvania, Ohio, were covered year-round in ice. That's only 6 degrees centigrade colder. Okay? London was covered in ice year-round. So all that you can really be sure of is if we are 6 degrees warmer, we will have an equally different world. A very, very different world. So I'll leave you with this. Another picture of the globe, this one taken by the astronauts of Apollo 8, the first Apollo mission that went around the moon. When the capsule came back and they saw this Earthrise, and what they saw was a very, very bleak lunar landscape, a very beautiful Earth, and the take-home message is, you better take care of this planet because there's nowhere else to go. So that's the question posed before this panel, is what is going to be our energy future? And if the picture I just gave you is our energy future and the future of the world, if the ship stays on course. Okay? And so the question is, can we turn it? How hard do we have to turn it? Is it possible to turn it? Are we going to have a bright energy future? So with that, I will start to moderate. And so I'll start with Dan Kammen. And let me just ask a provocative question. Some people say that conservation is all we really need. But let me just say, many people say that conservation is the most important thing we have to do. And the question is it really all we need? And so to start it off, I'll just let you start with conservation, and we'll take it from there.
Well, thank you all, and thank you for being here. Certainly, conservation, for some reasons I'll say in a second, is arguably the most important thing, not because it's the only thing, but because it gets us going, and I'll explain that in a second. But the other critical thing is that the IPCC, the Intergovernmental Panel on Climate Change, this group of roughly 2,000 scientists who shared the Nobel Prize with Al Gore, of which I and I think Steve and others were inputs to. So I guess we're micro-Gores in that nomenclature. Forecast that we need about an 80% reduction in carbon emissions by roughly 2050. And that just brings the risk of this iceberg disaster down to a risk between about 15 and 30%. It doesn't zero it. And that gives us a glancing blow, you might argue. And of course, anyone in the room who's an adult over that 25-year age point when they don't care about these would certainly buy insurance for things, and yet we have so far not bought any insurance for climate change. So let me just say a couple words about efficiency, because the real menu we need is going to be all of the above. And so to answer the question of the day, and I think everyone here is going to give the same first answer, because you wouldn't work on energy issues if you didn't think we had a potentially promising energy future. I think there's no question we do. In fact, assuming we solve this, which I believe we will be able to do, I believe we will look back from 2050 or so and say, Climate change, big problem, big change in the economy, big change in our science base, but small problem compared to the really big issues that we seem to have almost no means to address, that being global poverty and inequity. And so let me put in perspective why I think the energy problem is not very hard. We just refuse to do anything about it. Light bulbs that we all use, classic energy device. Light bulb isn't a light bulb. It happens to be a heat source. It's like having a hamster in your room and hoping you get a little bit of light out of the fur rubbing together. Light bulbs give off 90% of their energy in the form of heat. They're not efficient light bulbs at all. They're something else, and we use the accidental byproduct, essentially. Compact fluorescent bulbs bring that down. Light-emitting diodes, many of you have them on your flashlight chains, on your lights and stoplights and all kinds of things, start to get a point where the thing you're using for light is actually based on doing that. And that's 90% more efficient than a compact fluorescent. And there are wins like that all over the economy. There's a great story about refrigerators being made massively more efficient. There's a whole variety of these things. Smart lighting, smart heating systems, using waste heat from power plants, all kinds of things that are actually incredibly easy. We've just given our industries no strong signal to do so. The fact that we don't do anything to price the emissions, the pollution we put out into the atmosphere, maybe we'll get that in the next administration. I'm a senior advisor to Senator Obama, who I believe will be President Obama as of Tuesday. And he's committed to that, but it is going to be a huge fight. And pricing something new is like introducing a new currency. The number of things we can do to be more efficient are incredible. The California economy, New York, Rhode Island, Wisconsin, the few most efficient states are fully 40% more efficient than the national average. And yes, there is a red state, blue state difference, but we'll leave that for later. If all of the states were as efficient as those top states, and those top states actually have gross state products growing faster than the national average too, we would be able to remove the need to import any fossil fuel energy from outside North America. And that's not new technology we're waiting for. That's stuff we have today. So efficiency does an incredible job of getting us there. But we're also going to need a whole bunch of things. We will need solar. We will need nuclear. We will need a whole variety of technologies, wind, geothermal. We'll need a whole bunch of these things. But efficiency is the one that you can do it, and you save money day one. And most of the other technologies won't save you money day one. The fact, it's sort of sad that we have to look for that, but the fact is that we've got a whole range of these things out there. We have not put them into effect in any way near what we can do because we refuse so far to price the pollution. So there's a report that the American Physical Society released 3 weeks ago. It's called Think Efficiency. If you just do a Google for Think Efficiency, it'll pop right up. It's a report I had the pleasure to hand to Senator Obama about 2 weeks ago when we had a meeting on this topic. And it's the sort of thing that enables all of these other low-carbon technologies down the line because it wins right away, and it enables us to simply be more efficient about all of these new sources that will initially be expensive, not in the long term, but in day one they will be high cost. Efficiency is this huge win, and anyone in the audience who hasn't put in a number of compact fluorescent light bulbs and checked their utility bill a month later, you should do so, because you will save money in literally 1 month, even before the LED lights. So welcome to it, and I hope we talk about a number of these as we go.
Okay, thank you, Dan. So So efficiency is very important, but we really still have to use energy, and we'll continue to have to use energy. And so, Mike, why don't you talk a little bit about solar energy, which is actually, without insulting fission, I heard an interesting statistic. You have a nuclear power plants in the United States, and they're a plot of land, and the amount of solar energy hitting the property that a nuclear power plant sits on, if you convert 20% of that, 30% of that to energy, electricity, you would actually make more energy than the nuclear power plant. So, where do you think solar energy is going to go?
I think that solar is going to play a big part of the solution. the short way that I would describe the problem we face is that we need to provide now about 13 terawatts of power, but around 2050 that'll look more like 30 terawatts of power. And we have to provide that power without releasing carbon into the atmosphere. So that gives you the magnitude of the problem. And if you look at what the sun can provide, the sun is constantly giving the planet 120,000 terawatts. So we need 30, and the sun is providing 120,000. And of course, a lot of the globe is covered by water, but still, if you cover just 1% of the land with solar cells with 10% efficiency, you can get all the power you need. I don't think that we're going to have just one solution. The sun only gives us power during certain parts of the day, and as the weather changes, the amount of power we get changes. So we also need a good storage technology, but there are things like nuclear and fossil fuel powered plants that give us power whenever we want. So I think that there will be room for both in the solution. But it's really good to know, as we face this problem, that the power is there. And you have to ask a few other questions, like do you actually get more power out of the solar cells or more energy out than you put in? I hear some skeptics say that you don't. And that's just not true. It takes about 3 years to get the energy out that you put in, and the cells last for about 30 years. So you get 10 times more out than you put in. So it would be sustainable. And then it really just comes down to an economic question. And right now, it's about 3 to 5 times more expensive to get electricity from solar cells, and that's why we don't use it on a very large scale. But that's very quickly going to come down by a factor of 2 or 3, and we may close the whole gap. And in 10 years, it may be cheaper to get electricity from solar cells or solar thermal plants. So that gap's going to close. But even if it didn't, I'm almost sure we're going to get within a factor of 2. So we have to ask the question, would civilization as we know it be in serious trouble if we had to pay twice as much for energy? And I would argue that the answer is no. Right now, we spend about 7% of our gross domestic product on energy. And sure, no one wants to see that double and go up to 14, but it would not be a crushing blow to our society. I think that if we had the willingness to take that on, we certainly could. So as an engineer, I can say we have the ability to solve the problem, and it therefore really isn't a scientific question. It's more of a political one and one of policy. It's just a matter of getting people to be willing, I guess, to start turning the ship, even though everything is going fine and the iceberg is still pretty far away.
Okay, thank you. Lynn, the United States has more coal reserves than any other country in the world. And in fact, the United States, China, India, Russia have 2/3 of the coal reserves of the entire world. What do you think the future of coal is in this new world where we will try to turn the ship?
Well, we currently use coal to generate about half the electric power, just a little over half the electric power in this country. Though in California, it's a much smaller fraction. Here it's about 20%, and we choose to burn that mostly in Arizona and Utah. But if you live in the East Coast, the fraction is bigger. There's a big industry out there, probably 300 gigawatts or thereabouts of coal-fired power now. So we have a big job ahead to replace that. And boy, I hope Mike is right that that the cost of solar will be down within a factor of 2, because what I'm about to talk about, might very well put us in the same ballpark. So the question is, in the period where we take advantage of all the efficiencies that are out there, and I agree with Dan that there's a huge opportunity there and that we can all save money by doing it. But in the period where Mike brings the cost of solar cells down, we need to do something about all that coal that's out there now. So there are some possibilities. Here again, we'll have to decide whether we're willing to pay for them. It's possible to take the CO2 that comes out of a coal-fired power plant and capture it, typically by dissolving it in a solvent or sometimes by making it go through a membrane. And that CO2 then can be put someplace. The someplace that looks feasible at the moment is in the rocks that make up the Earth's crust. Now, there are multiple kinds of rocks, but sedimentary rocks typically are made of grains and they have little pores in them. And we have lots of sedimentary rocks in the United States, and some of those at least will be potentially suitable for storing CO2. Now, some of those rocks right now actually store oil and gas. And so if you live in Alaska or Texas or Pennsylvania, you might have actually been to an oil field. Those rocks are typically deep underground. They have some seal over the top that keeps those buoyant fluids in place. If that seal wasn't there, the fluids, the oil and gas would be long gone. So that's the kind of place you want to put the CO2, is in a rock where it will stay there. And of course, some of this carbon came out of those rocks, so it makes some sense to put it back. Now, we don't have oil and gas reservoirs all over the United States or even all over the planet. If we did, we wouldn't import so much oil from Saudi Arabia and Venezuela. So we'll need some other kinds of rocks or some other kinds of formations. And what I'm talking about is ones that are deep formations that contain salt water. They need to be deep so that the CO2 is at high pressure and is therefore relatively dense. And they need to be saltwater so that nobody's tempted to use it for human uses. Now, the CO2 that you inject in those formations will eventually dissolve in the salt water. And when it does, it no longer wants to escape upward. In fact, brine with CO2 dissolved in it is actually slightly more dense than brine without it, so it actually goes down instead. But you need time to do that, and so you have to make sure that seal rocks are in place in order to keep it in place for a time. We do have lots of those rocks, though not every place will be a sensible place to put it, and we'll have to look very carefully at them. Turns out that you can also take advantage of forces that that involve the surface tension between water and a supercritical fluid like CO2. These forces will act to trap little bubbles of CO2 in the rock, and once they're trapped like that, it's really very hard to move them. So there are some mechanisms that can isolate that CO2 and keep it there more or less for geologic time. It's also possible to store CO2 by sticking it onto coal particles, but again, you'd want to do that only in deep coal beds that couldn't be mined later. So there are some places to put the CO2. We'll have to engineer carefully the capture systems. Those will raise the price of electricity by say 25 to 50 to 75%, depending on the setting. So there's if we charged ourselves something for carbon emissions, Mike's solar cells would look competitive in that system if he can get the price down to a factor of 2 from where we are now. We'll also have to monitor where the CO2 goes and be prepared to fix problems if they occur, and engineer and operate these systems safely. This can be done at scale. We have about 35 years of experience of injecting CO2 at big scale for enhanced oil recovery in West Texas and Alaska and a few other places around the world. And there are 3 or 4 big demonstration projects around the world that put away about 1 million tons a year of CO2 now. We need to demonstrate that at scales that are the size of a 500 megawatt plant, which would be probably 3 million tons a year. But there is some possibility of some things that we can do in the period where we have not yet divorced ourselves from coal. But I think we do need to do that. We do need to move away from these fossil fuels. This is the century where we humans need to demonstrate that we can live on this planet in a way that we can sustain. And we have a way to go on that, but I think we can do it, and it's time to get to work.
So we've just heard that coal has potential if we can make it clean and capture the CO2. Solar has potential if we can make it less expensive. What about fission? When I was a kid, Per, I was told fission is going to make electricity so cheap you don't even have to meter it. And let's see, I think it was 1973 when the last fission reactor we're now using was started.
That famous quote actually was predicting that fusion would be too cheap to meter.
Ah.
Yeah, it's not commonly appreciated. So I'll answer that question by actually discussing a bit about the history over the last 25 years of what's happened with nuclear energy, because it's actually quite relevant to the question of what's changed and where things might go in the future. To start with, though, just the most basic way you can describe nuclear fission as a source of energy is that it consumes very, very small quantities of resources in the process of producing energy. And we know that that's the case with fuel because you have energy densities that are 1 million times higher than those of fossil fuels, and therefore you have a fuel source where it's practical to have an extraordinarily small waste stream. If we decide to recycle it, it can become yet smaller, but it's something that can practically be put into deep geologic isolation under conditions that would be similar to, in some ways, arguably easier to predict, and if you needed to in the future, easier to reverse than the sequestration of carbon. Sorry. Let me just put it right about here then. So the inventories of fuel that nuclear power plants consume are very small, and that makes it practical to use deep geologic isolation for whatever residual wastes you have, and you will have some that will require it. Another thing that's not widely known is that the amount of material it takes to build nuclear plants is also quite small. In fact, it takes about half as much material to build a nuclear plant in terms of steel and concrete as it does to build a pulverized coal plant. Without any carbon capture and sequestration. The thing that makes nuclear expensive is the fact that it has to be done very well. That is, the regulatory requirements and engineering requirements are much more strict in order to do it well. And so if we go back in history and ask the question, what has changed over the last 25 years that could influence the role that nuclear might play in the next 25 years, probably the most important thing relates to how well we can operate plants. So if you go back to the mid-1980s, in the United States, average nuclear power plant capacity factor was about 65%, which means that back in the 1980s, with our fleet of about 110 plants, on average about a third were down at any given point in time for forced outages and very long refueling outages. The major transformation that occurred over the last 2 decades is in the capability of utilities to operate the plants far better than they used to. And most of this actually had to do with understanding how to be much more sophisticated about human factors and how it is that humans work with technology and developing things such as safety culture as a concept, which in fact then relates very strongly also to the reliability of the plants. And so today in the United States, the average capacity factor of the existing fleet is 90%, of which less than 2% is for forced outages, and the remainder is for relatively short refueling outages. And this is frankly a transformation in the capability to operate these plants. Now, the really big question, and whether they can contribute, nuclear can contribute in a significant way to getting the ship started to turn, is whether or not we can now build new plants with the same level of competence that we can run them. And this question is still open to debate, because it's something different to build new plants than it is to run them. And we did not do a great job of building new plants back in the 80s either, if you go back and look at the history. And if we were to repeat that sort of history, nuclear will have no significant role to play. But if it can be done well, remembering the fact that it takes less than half as much stuff to build a nuclear plant than to build a coal plant. And in China, they're putting in 100 gigawatts a year of new coal capacity. You could build a lot of new nuclear plants too, but only if we learn how to do it well, which means things such as using modern modular construction and factory prefabrication and a variety of other techniques. And we'll know within 10 years pretty well whether the industry is capable of doing that, because we're poised to build a number of new plants here in the United States and worldwide, and we'll see how it goes. I can't predict for sure, but the potential exists that it could provide a significant contribution.
Now, when I listen to my panelists, and I also have to say that I too, all my panelists do research in various forms of energy, whether it's on the supply side or the demand side. But when I listen to them, it sounds as though we're good to go. We've got all the technology. All we need is a little bit of political will. In fact, Al Gore has said that in 10 years we can go to carbon-free energy in the world. And so this is a rhetorical question, but number one, we'll start with you, Mike. Are we good to go, or what do we really need in the future?
We're ready to start shifting, but we couldn't do it overnight. If we were to get, say, a third of our electricity from solar, it would just be impractical to do that in the next few years. Even if we were highly committed, it would take a long time to build all those factories, to mine the materials that you would need, to train all of the people who would go install the solar cells. And part of what makes ramping up difficult is it would be incredibly risky for any business to spend many tens of billions of dollars guessing that an industry would grow by, say, 1,000% a year, because if it didn't grow by that amount, then they would lose an enormous amount of money. So it's very rare that industries can grow much faster than a couple 100% a year. Maybe you see that with computers because you're not, or at least with software, you're not actually manufacturing something. But when you're building factories and actually making stuff, you can really only grow, 50% to 100% a year. And like right now, solar provides such a small amount of power that it would take about 15 years. And also, I didn't say we had matched the cost now. I said I thought we could do it, but still a significant amount of research would need to be done in order to close that gap between what electricity from solar costs now and what it costs from a coal-fired power plant.
Dan, what do you think in terms of energy efficiency? Do we have all that we need? Insulation is old hat?
Right. Well, we certainly don't have all we need, but the answer to this question is a very simple yes. We have more than we need to get going, because we don't need to solve the problems of 2030 today. We need to get the economy building clean energy. Efficiency is this great jump start in the process. It makes everything we do much cheaper. I have colleagues in engineering departments at Stanford, MIT, Cal, elsewhere, who are finding ways to replace essentially all of the conduit and all the wiring in building with low-cost sensors, and dropping the cost of building buildings in very large amounts and making them cheaper to operate. So we have all the tools we need to start. We don't have all the tools we're going to need by 2030 or 2050, but let's solve that problem when we get to it. And pricing greenhouse gas emissions and requiring us to do so, and since the United States is the biggest driver of research and development in the world, and yet we have been essentially absent from the global dialogue for, say 7.99 years. And we were no better before that. President Clinton was unfortunately as much of a failure as President Bush. In fact, more got done under the opposition movement, state by state around the country, under Bush than under Clinton. We need some guts, we need some fortitude, but we have the technologies to get going. Whether we build lots of nuclear plants in 10 or 20 years, whether we are building carbon-free coal plants, we have the ability with solar, with wind, with efficiency to start the story now. And this point that Mike and Steve alluded to about the price difference to get us going isn't that big. In fact, it's the certainty in the market. If we knew there was a carbon price, if we knew there'd be requirements, it's very easy to get this game going. We just haven't shown the collective guts yet.
Okay, I'm going to get a little tougher with my questions because these guys have been a little too vague. Okay, so, sorry. I want to pin them down actually on what it is that needs to get invented or what it is that you see as on the horizon. So with you, Lynn, carbon sequestration people talk about, and the prices you were discussing were, if everything works well and you scale up by a factor of 1,000 or 10,000 and drive the price down, this could happen. But what could go wrong? And what are going to be some of the issues in the capture and the storage and sequestration?
Yeah. Well, there are plenty of barriers. There are plenty of things that we have to work on. I just would echo that none of this happens if we don't set a price on carbon. There's no incentive. In fact, right now, public utilities commissions have, in some places, refused to let utilities spend money on being ready to capture carbon because it increases the price of electricity, and they see their job as keeping the price low. So we have to make up our minds that we're going to do that. But there are plenty of technical barriers as well. When you separate the CO2, there's an energy penalty. It takes energy to do that, and that's one of the reasons the costs go up. So research there could help us bring that cost down dramatically. We'll have to move some CO2 around, which takes pipelines to do it, and that will take right-of-ways, and those are tough to sites. We will, to accommodate Mike's solar, we'll need a much better grid than we have now. Even if there's lots of wind and nuclear, we're still going to be able to need to move power around in lots of ways. And we're going to have to demonstrate to the world that we can do this geologic storage in a big way and do it safely. And I will say that this can't be the only thing we do. I mean, nobody has said that it would, but we really do need a portfolio because the numbers are absolutely staggeringly large. So just to give you an estimate, so the United States probably does 7 or 8 billion tons a year of CO2 emissions. If you just take 1 billion tons of CO2 and you convert it to the density that we would typically use in the subsurface, you're talking about 30 million barrels a day in the silly units we use to describe oil recovery. So the United States uses 22, well, before the current recession, 22 million barrels a day. So we would need an infrastructure to do 1/7 of U.S. emissions that's bigger than all the infrastructure it takes to move all that oil and gasoline around the United States now. So this is not a small deal. So when I say it can be one of things, it needs to be one of 30 things we do to reduce emissions. We shouldn't take it as a panacea. But I do think it can be done at scale. We have enough experience to say that it can be done that way if we're willing to pay the price.
Let me interrupt you for just a moment. I've just looked at the clock, and I want to make sure the audience gets enough chance to ask questions since we started a little late. So after Paris speaks, can we just take audience questions? Very good.
Very good. Let me throw in my 2 cents on the same question. First of all, I would echo every other speaker here that the most important thing we need to do if we want to control carbon emissions is to control carbon emissions by increasing the cost of emitting it through cap and trade or a tax or a combination. That's the most single fundamentally important thing that has to happen within the next couple of years, because otherwise investments are not going to be made. The next thing that I would point out is that the magnitude of the financial investment needed to build the infrastructure that can provide this low carbon electricity is too large for utilities to be able to purchase it. That is, their capital values are too small for them to be able to financially get the funding needed. And so the second thing I think we need to do is to expand the current loan guarantee program, which Congress has authorized at a level of $38 billion to perhaps $200 billion, so that utilities will be able to go forward with substantial investments in new infrastructure. And then the final thing, if I were to think specifically about nuclear energy, is that we do need to make progress on the waste question. And the Department of Energy has docketed a license application with the Nuclear Regulatory Commission for the Yucca Mountain Repository that shows compliance with a 1 million year safety standard that meets the requirements established by the recommendations established by the National Academy of Sciences in a 1994 report. And I think it's also very important that we allow that independent technical review to go forward rather than interfering with it sometime in the next few years politically, so that we can make a decision on whether and how to use Yucca Mountain based on the results of this independent scientific and technical assessment. And I think that that's a vital thing to do. Our current policy for how to use Yucca Mountain is poorly formulated, but the technology behind that site appears to be strong. And so we need to make sure that we get the independent assessment completed by the U.S. Nuclear Regulatory Commission. And I think that's one of the most important things we need to do on the nuclear side.
Okay, so are you going to handle questions? Am I going to handle questions?
They will. I'll use this microphone, and I'll ask everyone to talk to the hand.
Okay. So anyway, so throw it open.
All right. I'll start. Anyone in this quadrant here? I have. Okay. All right. Well, I can hear loud enough. What we want to do is make sure that the cameras can pick up the sound for later. So I'll start on the far left, the second man from the aisle. Did you hear the question? Would a simple carbon tax be easier to manage and control?
A simple carbon tax would be easier, but politically much more difficult. They say that tax is almost a four-letter word. And a carbon cap and trade system is politically easier. But note, if you give away the rights to permit, if you give away those permits, then a cap and trade is really a talk and delay strategy. And so the real issue is, do we have enough guts to stick with it? If we don't, tax would be much better. In fact, economically, it's the simpler way to do it, but it's very unlikely that we would be able to get a tax through. Europe tried for 10 years under a much more green-leaning economy and failed. And if you think we're going to beat that down with a huge coal dependence, it is unlikely to happen. So we don't want to make the ideal the enemy of the good in this case.
Okay, I thought I saw a little hand go up way at the top in the top section. Yes, sir. Three? Well, we'll bargain here. Maybe I'll give you two.
Well, my first one is for, I'm forgetting your name, the green shirt?
Lynn.
Lynn, yes. You're trying to put all your questions in the one, aren't you?
I got it. Okay. Is there any way to recapture the emissions that are already in our atmosphere?
Oh, so that's a great question. The question was, can we do something about the CO2 that's in the atmosphere already? Actually, Mother Nature has lots of ways to do that, and there's a really very interesting device. It uses solar energy, and it takes CO2 right out of the air, and it stores it in chemical form. We call them plants. But they do so sort of slowly, and we're pushing CO2 into the atmosphere more rapidly than they can take it up. The oceans also take up CO2. But your question is actually a good one. There are ways we could make chemical solutions that would react with that CO2 and make it minerals. The trouble is they go sort of slowly when the concentration of CO2 is not very high. And while we've increased it in the atmosphere, it's not very high compared to the exhaust gases of, say, a power plant. So
it's usually cheaper to go after the higher concentration sources first.
Okay, we have so many people asking questions. That's going to have to be your only question there. The blue shirt, sir?
Yeah. So it sounds like a lot of the topics that we're talking about all need some sort of proper pricing strategy, whether it's a carbon tax or cap and trade or whatever. And I'm just wondering, how do each of you value the future? And does that agree with concepts of devaluing future money?
Well, let me start on that, and maybe the others can chime in. You, by the nature of the question, you know of the economic debate between some economists. And in devaluing the future, we have to be a little bit careful. And that is to say, if you take money now and invest it now in something, the question is, as you go further in the future, we can get smarter. We can have better inventions, better discoveries that could make it cheaper to do things in the future now. And there's something called lost opportunity cost, because if you invest money now, there'll be greater wealth. You'll have greater wealth to invest in solutions in the future. So it gets really back to this Titanic analogy. You can start turning now, or you can do hard right rudder now. If you do a hard right rudder now, there are costs that you're going to pay now. If you do gentle right rudder, maybe you won't turn in time. And so there's a debate between, let's say, Nicholas Stern, who says you essentially don't discount the future, that the lives of grandchildren born, of people born today are, and going forward 50 or 80 years, are equally as valuable as an 80-year-old today. Mainstream economists actually say no, that it's discounted because of that so-called lost opportunity. And it actually very quickly boils down, in my opinion, to a ethical question as to whether someone unborn today or just born today is really going to be valuable. But it's a legitimate debate among economists as to whether, because of lost opportunities of delayed investment, would be better. But other panelists have...
It appears Per has something to say there, yeah.
That's a really good question because, of course, the discount rate that we demand for different activities really depends on the activity. Businesses need a higher discount rate, and it makes sense. When we educate students in the kindergarten, if you were to make a business calculation on whether it makes sense to spend money on that activity, it wouldn't, but our social discount rate for education is much lower. I work in an industry where we have a discount rate that is so low that we worry about things a million years into the future. And we're unique that way. For chemicals, the EPA does not have any regulations that extend past 10,000 years. And for most hazardous chemicals, most of which remain hazardous in perpetuity, the typical time period that people worry about is a couple hundred of years. So we're used to the idea of establishing very low discount rates and paying for things up front to protect people into the distant future.
I think there's one important thing we're missing in this, however, and that is that nature doesn't give a damn about our economic discount rate. Nature cares about the amount of greenhouse gases in the atmosphere, and there's two things going on. There's the gradual warming, but there's also the so-called tipping points. There are certain bad things that are lurking out there, like the circulation of the ocean potentially turning off, or the ice sheets melting to a degree that absolutely changes basic features of the planet we live on. Nature cares about the raw amounts of greenhouse gases, not about whether we're making 6% or 7% in our CDs. And all the economic analysis that you hear ignores these nonlinear events, these tipping points. And buying some insurance against those tipping points is worth a massive amount that we leave out of this discussion. And so there's an unfortunate side of the classical economic argument, no matter how good your dithering around a given number is, whether it should be a 3.2% or a 1.9 or whatever else it is. We're missing something basic about nature if we boil this argument down to an economic one.
I'm actually side with Dan because if we don't do something about this starting today and starting very hard, the ship can sink.
Okay, Lynn?
And that's the issue.
So one more way to say something that's similar is to say that you know, the planet provides us with a whole host of services that we take pretty much for granted. And one of them is its temperature, but it's not the only issue that's important to us. All that CO2 that we've pushed into the atmosphere is happily dissolving in the ocean, and when it does, it reduces the pH. And what that does is to change the concentrations of ions that are very important to all the little critters that make calcium carbonate, the stuff of shells or coral reefs. And that influences the phytoplankton that are at the base of the food chain. So everybody in the ocean eats them or eats somebody who eats them. So what we're really starting to do now is to mess with systems that really do provide essential services to us. And so another way to say all of this is that we need to value those services as we think about all these other economic issues.
There's one other economic issue, and that's conservation. I have a friend by the name of Conyers who was very upset with his wife because she kept buying $400 shoes. But she pointed out to him that she was waiting until those shoes were discounted to $200. So in fact, she was saving him $200. And she bought so many shoes, he was able to retire early. So, so the question is the economic question is conservation. When we assign a percentage to how much solar contributes, how much nuclear might contribute, conservation contributes what? Or is that just a drop in the bucket?
No, it's huge, actually. Conservation actually is the single biggest payout we get right now.
It is.
Not because all these other technologies aren't critically important, but because efficiency saves the quickest. It has the fastest payback on the investments. Now, there are some long investments. There's many things we do right away that we can save. We waste, of course, huge amounts of energy, not just with wasted light bulbs, but because thermodynamics means we have to discard heat, and we discard 2/3 of the energy in most of our processes. So capturing that heat is something that places like Denmark and parts of Russia do to heat their homes. So we can be massively more efficient and save money essentially the next day. Most of the other technologies will take these paybacks.
I'm actually not speaking of efficiency. I'm saying choosing not to drive, choosing to turn off lights, just lifestyle changes. Is that unrealistic to expect that to contribute?
It's not unrealistic.
No, it's not. Let me give you an example. So I was putting in a solar PV system at our house, so of course I looked at the utility bills for the last several years. And then during all the time it took to get the permits and install the darn thing, I started looking at where the heck all that electricity was going. And by the time I got done fiddling and deciding only to heat the rooms that we were in and turning off the ice machine that we hardly ever used and on and on and on, we had reduced our electricity use by about 25% in our house, and without really sacrificing anything in terms of comfort or the way we live. So there are huge opportunities, at least if you were as wasteful as we were.
Let me try to drive home the point how important efficiency and conservation are. Our refrigerators, as Dan said, have become very much more efficient. They've been a factor of 4 more efficient since 1975. Now, if we had the refrigerators of 1975 in our homes today, we would be using an amount of electricity that's twice, we've saved twice the amount of electricity of all of solar thermal, all of solar photovoltaic, and all of wind in the United States. Just refrigerator efficiencies has saved more than all that we generate by all those sources. That's how important efficiency is.
Okay, I'm sorry, we started taking things away from the audience here. I'm guilty of that. Yes, sir, in the blue shirt.
What about fusion? I mean, R&D and fusion, that could be the magic cure for everything.
I've worked on fusion as well, and we are getting closer to demonstrating scientific viability of fusion by both inertial and magnetic fusion routes. The next step will be to demonstrate engineering viability, that is, to actually produce power, and then to compete economically. And that process, Dan and I will sort of place as being somewhere 30 to 50 years in the future. To get
but it's not stalled? Would you describe it as?
It's underinvested in, but relative to everything else we do with energy, we have underinvestment across the board. So we could be doing certainly more now in that area.
Can I tell one-minute story about fusion? And that is, I was at a U.S. Senate hearing about 9 years ago when the senator asked the director of the Princeton Plasma Physics Lab, at what funding level will the U.S. fusion program go under? And the individual unfortunately chose to answer. And he said, well, at about $210 million a year, the program is so subcritical, it's not going anywhere. The next year, the program got $213 million.
Excellent. Okay, we have one question here, sir. Yes.
5 years from now, what do you predict will be the price of a gallon of MoGas or a kilowatt hour of electricity, and what ought it to be?
What's MoGas?
87 octane car gas.
Well, forecasting, predicting.
Around $4 a gallon in 5 years' time.
Okay.
What should it be? Around $10 a gallon.
Yeah.
Okay.
Yeah. All right. I want to get some more questions in here. Yes, sir.
If nature's so important, shouldn't we just plant more crops and get rid of world hunger along with carbon dioxide?
Okay, plants serving a dual purpose. Why don't we just plant more things?
Well, the plants on land exchange about 60 billion tons a year of carbon, so it's almost 4 times that if you think of it as CO2. But they're almost in balance. That is, the plants take up a little more CO2 than they emit. So if we were going to somehow capture all the carbon that's emitted around the planet, we would have to have a quite big expansion of the productivity of all those plants. Never mind whether or not we actually feed all the planet and worry about the water it takes and the fertilizer and so on. So biological systems do have a place in all this, but they're going to be a relatively small part of the overall system just because of limits on land. Actually, Steve, you might want to talk about this too.
Well, see, what happens is when you have plants, what they do is they take sunlight energy and they grab carbon dioxide out of the air, they combine it with water and other nutrients, and they store it into this chemical fuel. Now, when they die, several things can happen. Either someone or animal eats it, or a littler critter, a microbe, a fungus, a bacteria, quote, eat it, and they recycle it back into stuff that ends up being methane, carbon dioxide. And so the vast amount of that, 99 point some other fraction %, just goes cycling back and forth. When you have a forest, when you first plant a forest, as the forest grows up, it's storing carbon dioxide. But after you get to a mature forest, then you get to steady state. There is some hope of altering the plants or the little critters that Lynn talked about, so that some of that gets mineralized and gets put underground by the plant, by chemical reactions with the plant. So you can actually store net carbon dioxide. And actually at Lawrence Berkeley Lab and other places, we're looking into ways of just adding a little bit so that it doesn't just cycle around.
Are you talking about botanical sequestration?
Yes, yes.
Genetic engineering?
Yes. Or it doesn't even have to be genetic, and it can be bred, or we're actually doing a little project that got a little laboratory director funding where if you take gypsum, which is this stuff that comes out of fly ash and just concrete filler, and you sprinkle it in forests, it may actually induce the trees to fix more carbon dioxide and mineralize it. So it doesn't have to be genetic engineering. In fact, it could be bred, it could be a lot of things. It could be changing the ratio of nutrients.
Okay, well, I'm going to get as many questions in as I can. Far corner, sir, yes.
I like the point about the insurance and the tipping point. I think that's absolutely critical and is very much understated by this panel tonight. I'd like to ask you, what do you think the price of carbon per ton needs to be 4 years from now to really give us 90% confidence that we're not going to collide with the iceberg? And then what do you think politically it will be for you?
Now, I just want, for the rest of you, you're talking about carbon penalty price.
Whether it's cap and trade or
Okay.
what the price on a ton of carbon should be.
First, we are going to collide with the iceberg. There's at least 1 degree centigrade built into our system. If humans stopped emitting all greenhouse gases today, we'll go up by 1 degree centigrade. And so the real thing is whether we're going to go up 2 degrees or 4 degrees or 6 degrees. Okay, so we're going to hit the iceberg. So okay?
The question is it a glancing blow? Do we get a so-called soft landing, or do we get a abrupt landing? There's no real answer to this because we don't know the probability of those catastrophes. If you assume the kind of gradual warming increases costs, and so we smooth out Katrina-like events. So we kind of we do the broad version of this. The estimates from our group and a number of others are that the price of carbon probably needs to be, not what it will be, but probably needs to be more than about $40 a ton. Now, that's not very much. In going from $2 a gallon gasoline to $4, that was almost a $300 a ton equivalent carbon tax. We didn't do it for greenhouse gas reasons, but that is a sort of feeling for it. It doesn't have to be that large, but it's probably the case that the most important thing is that we have a price at all. It's the little bit pregnant argument. The price might not be what I want, but we need to have a price. And as long as we sit on zero, we send all of the wrong signals. And Per and others said, whereas we essentially right now encourage companies to emit. And so there is a real issue of getting it going at all, even if the price we get soon isn't the one that we estimate we need in terms of what level of price will make solar more viable and will get a wind industry in this country really started on a large scale. So two sides to that.
Can I add a little bit to this? This is not my opinion as a scientist, but if you start a price now and say, for sure in 10 years it will be something substantial, $40 a ton, let's say, in 10 years, and then it might go even higher after that. But there's no loophole, there's no going back. Industry will actually start to make very wise investments immediately. And so you don't really have to shoot it up today suddenly. You can actually say, in 10 years from now, it's for sure going to be there.
Yeah, I think $40 a ton is way too low personally. And you were saying $10 a gallon for gas is probably what we need. Other people suggested that we should go maybe $240.
So we use carbon dioxide and carbon.
Sorry, I was talking in terms of carbon.
Not
Carbon dioxide price multiplied by 44/12.
Yeah, but you're used to thinking, that's why I scratched this when he was talking, with carbon dioxide versus carbon.
Okay, I have to move this along because I notice people looking at their watches, and I know some people want to leave, but they're too polite. But I'm going to limit it to two more questions. And you've had your hand up all night, sir. Way up in the back with the glasses. Yes. Right. No, no, wrong glasses. Yes.
You talked about pricing carbon, but for more of what we can do now, is this something that has to be approved by the U.S. Congress, the state of California, put in the policy? I mean, how can we actually get this idea started?
There's a couple things going on. There are already carbon prices popping up. California and the western states and the parts of Canada that have now decided to join the western states are already having a discussion for how to start that. That price of carbon will start within the next 12 months. In New England and the Mid-Atlantic states, they've already started a price for carbon. Unfortunately, they forgot a minor part of the story. They're only charging their price of carbon in the Northeast for power plants, and yet we emit carbon from our vehicles, from moving goods and services, so it's an imperfect version. Europe already has one, so there are a number of these coming, and the issue is how quickly do we build a much broader trading system? So we have the signs already, and we have nice experiments, but it takes real leadership to add a new currency, and adding a price for carbon is like, we're going to start printing dollars and printing these carbon things, and it's a big deal to take that next step.
All right, I'm sorry, I have to interrupt right now. I've gotten the sign from Tucker. We've gone way over time, and I know you people have families you have to get home to. So I want to thank you for donating as much time as you have right now. Ladies and gentlemen, Paul. I think this was an exceptional panel. You guys were just great. You're perfect. Thank you very much. I want to remind you, if you can't make it to Berkeley tomorrow, call a friend, have a friend go for you. There's more Wonderfest at Cal tomorrow. Thank you all very much for staying this late.